So for the first set of examples here, you have to decide which of the numbers are rational and irrational. So the first one, square root 6. If you actually punch that into your calculator, the number you will get is 2.44948. So there's nothing tidy fractional about that. It carries on, by the way, 9, 7, blah, blah. And because it does that, it's irrational. So there's no pattern to the decimals, and it doesn't look like an obvious fraction. So that one's irrational. Any whole number for the next one, -5, is already a fraction because that can be made into a fraction out of 1 if you want to see it in fractional form. So that one there is rational. 2 pi, now pi has an endearing irrational quality to it. If you were to put that in your calculator or find the pi key, pi equals, you will find that pi equals 3.141592654 and so on. Just because we're doubling it doesn't do anything to it, so it remains irrational. So that's one to learn, that pi is irrational. The next one, 2 3/4, is already a fraction, and we can change it into improper fraction. So 4 2s are 8, 8/4 for the 2, and 11/4 is what we could also change it into. But that's obviously rational because it's already sitting in a fractional type form. The next one here is something that tends to repeat, which you may know as a recurring fraction, and because it just has that pattern, that means that that one there is rational. It can be changed into a fraction. This next one here is the cube root of 27. So you will find that the cube root of 27 is equal to 3, which is a rational number. At this stage, go and make sure you know which buttons to press to do cube roots in your calculator. 0 is also rational. That one we decided was rational. -1/2, it's fractional, rational, and cube root of 2 is the last one. If you pop that one into your calculator, you will get a number with lots of decimals that don't have any pattern to them, which makes it irrational as well. So you just need to, again, pop that into your calculator. For this next little package of examples, they ask for the surds. So surds are numbers that cannot be evaluated to give a rational number. So we're doing the same thing as before. Square root 2 becomes irrational if you punch that into your calculator. So it is a surd. Cube root 27 is not a surd. Square root 12 is a surd. Square root 25 becomes a whole number, so it is not a surd. And cube root 6 is a surd. And the last one, 4 times. Now, if there's a number next to a surd, this is what it represents. So this whole thing here is 4 times the square root of 3. 3 square root is irrational. It's a long, horrible, repeating number. So that one there remains a surd. So most of them are actually surds, except the ones I put crosses next to. In this next example set, and that one matches up to question 5, to find approximate values, you just use your calculator to punch them in. So make sure that when you do square root 2, you get that rounded to 3 decimal places. Square root 12, you get 6.928, and so on. Just make sure you can do those, and it's a very simple approach. And I just want to say that finally, on this example here, when we have rational approximations, these numbers are not as good as the original surds. They lose the meaning that was there. They're approximations because we can't capture the whole crazy irrational number. We've kind of just rounded it off. So that's why they're called approximate values, and that's quite important actually. So they're never going to be as good as representing them in surd value as the top line, but they're kind of approximate. So there you go. You can have numbers that are not exact in mathematics, and surds are a case of that. Okay, so an equivalent surd is a number that's in surd form where we can square root or take out part of that number to become 3, and some of it remains as an equivalent surd. So what they've actually done here is they've said that 18 is the same as 9 times 2. Okay, so that's 18 inside the root symbol, and that's the same as square root 9 multiplied by square root 2. Square root 9 is 3, and square root 2 we can't do, so it just stays as square root 2. So we just represent that as 3 next door neighbours means multiply, square root 2. Another example that may or may not be in your book that we can do is square root 28. What we need to do is, if we want to write an equivalent surd for that, is we need to just eyeball it and see if there's any square number that we can pull out of that. I know 7 times 4 equals 28, and I know that 4 is a perfect square. So let's pop that inside, inside the surd symbol. Square root 4 times square root 7 is the same as square root 28. So we're just respectfully kind of expanding that, if you like. And square root 4 is 2. Square root 7, we can't do much more with it without it becoming irrational and lost. So we can just write it as that. So that's equivalent to square root 28. One more example, in case you're not 100% sure on these ones, is, I'll give you this one here, square root 50. So we're looking at the number 50, and we can either do a tree or something, a factor tree, to see what the factors are. And what we're hunting for, 2 is irrational, but 25 is actually a perfect square, which is really nice. So square root 50 is the same as 2 times 25 in the squared sign, so that we can split that out to square root 2 times square root 25, and square root 25 is just 5. Square root 2 stays the same. Okay, I'm just going to write that with the whole number first and the surd on the outside. So that's just another example for you. So this next example here follows on from that, where we're simplifying the surds. Now, simplify simply means writing it as simple as possible. So we're going to take every single perfect square out of the number. So for A, 50 is 2 times 25. I probably should have written 25 first, because square root 25 times square root 2 is 5 times square root 2. For the next one, we look at it and we could be fooled to say, well, hey, there's a number outside the surd sign and there's a number inside. So that one we can't do any further. But let's just eyeball that and see if we can find any perfect square numbers within 45. If we look at the factors of 45. 9 times 5 is 45, and 9 is the perfect square we're looking for. So this deal here becomes 2 times square root 9 times square root 5. So we're sort of really pulling that 3 out of there, 2 times 3. And the square root 5, we're just going to leave it in surd form, so that's times square root 5. And that whole thing simplifies to 6, so we just multiply the two numbers in front together, times square root 5. Another situation they ask for is an entire surd. So they don't want any spare parts outside of the surd sign. So 5, now this business here inside the square root sign so far is just 2. 5, if you like, we need to put it into square root form. So we're just going to square it up. We're just going to go with 5 squared, square root. Hang on, I can't write in that corner of the space. So let's write over here. 5 squared square root is 5. Because if we square it and square root it, squared is 25, square root takes us back to 5. So anything that is squared and square rooted is itself, is anything. Okay, so what I'm going to do here is I'm going to square it and stick it inside the surd key, the surd sign in here. Okay, so that's what I've done there. So that's 2 times 25, which is square root 50. We've seen this example before, so it shouldn't be too hard. It's just the way we unpack it. Okay, so we square it up, stick it in the surd sign as 50 25, my bad, and we multiply it by the 2 that was already inside the surd sign. We've made it an entire surd now, so it's sitting inside a surd sign. Okay, next one, 2 times square root 11. We're putting 2 inside a square root sign, so 2 squared times the 11 that was already in there. 2 squared is 4. 4 times 11 inside there, which is square root 44. Okay, for the last skill that you're going to need for this section of work for 4.1, for exercise 4.1, is taking a number like 360, and they ask us explicitly to write it as the product of its prime factors in index form, and then to express the square root of 360 in simplified surd form. So the first thing we have to do is do the prime factor expression. So we can actually do that as a prime factorization. So I know 3 12s are 36. So I'm just going to find the smallest numbers that I can out to the side here. And I also know that 3 4s are 12, so 3 times 40, 5 8s are 40, and then I can pull 2 4s out of there and 2 2s. So there's my prime factor tree. So I've got base 3 twice multiplied by base 5 just the once, and that's multiplied by base 2 1 2 3 times cubed, like that. So now I'm going to put this expression inside the square root key. So I'm going to write square root of 360 can be written as, I'm just going to change pen color, as 3 squared times 5 times 2 cubed. Now, as much of that as I can square, the 3 squared is beautiful because I can actually square that. I'm just going to park that for now. The 5 I won't be able to. The 2 I sort of can. So here's what we're going to do. 2 cubed is 2 times 2 times 2, which I can also split out as 2 squared times 2 to the 1. So remember, when we have power 3, we can break that down into 2 plus 1, because when we add powers, we can simplify as 2 cubed. So I'm going to split that out as 2 cubed times 2 to the 1, simply because I'm now hunting for things I can pull outside of that surd sign and square root them, basically. Now I'm yet to square root that, so I'm going to keep this surd sign in place. And what I'm going to do is I'm going to pull the 3 squared out of that just to make it 3. So once I've square rooted it, it becomes 3. It's gone. The 5, I can't do anything with it, so it's going to stay inside the surd sign. The 2 squared can come out, so when I square root, so remember it's in a square root sign, so when I square root 2 squared, I'm very simply left with 2 on the outside, and the other 2 to the 1 stays inside, so we can just write that as 2. We don't need the 1 really, so we don't have to write it, so we just do that. So ultimately that becomes 6 times square root 5 by 2 inside the surd sign, which is 10. That's the very simplest I can do, keeping everything really clean. So that's quite a methodical process. So you can either stop here, or I'm going to do one more example of this type for you. A similar example that I'm going to do a prime factorization activity to see if we can simplify the number is this example here. I'm just making this one up. So we're going to do the square root of 120 using the same method. So we're going to find the prime factors so we can get this down small. So that's a little trick for cleanly getting everything out of the surd sign as we can. So we want to find the smallest pieces, the smallest components. So let's work the way through. So we'll do prime factor key, prime factor tree. 2 times 60 is 120. 60 is also made up of 2 30s, 3 lots of 10, 2 lots of 5. So here we go. I've got base 2 3 times, and my prime factorization then is times 3 just the once, that guy there, multiplied by the 5 also once. So what I need to do is pop that prime factorization output into my surd sign to square root. Okay, and let's see how much of that we can tidy up. So 2 cubed is 2 squared times 2 to the 1. 3 to the 1 I can't square, and 3 to the 5 I also cannot square. So the only part of that I can pull out is that. So I'm going to pull it out to the front as 2. And I'm just going to put this back for you so you can see what I've done there. And then the rest of it stays inside the surd sign. So it becomes 2. 2 3s are 6, 5s are 30.